we can calculate the heat of reaction from standard enthalpies of formation that other people have determined. So instead of having to do the reaction and measure it yourself, we can use Hess's law and data either from the internet or from a resource like the CRC Handbook of Chemistry and Physics, and we can calculate the heat of reaction. So how does this work? Well, delta H is change in enthalpy. We can't measure absolute enthalpy. Enthalpy is a relative thing, just like elevation is relative. So we can decide to set 0 wherever we want, and we can decide to make it convenient, right? Sea level is considered the reference point of elevation. Why? Because it's convenient, right? The ocean, being liquid, is fairly level across the globe. And so if you're in Italy or you're in California or you're on the coast of Russia, you can have sea level and you can measure in reference to that, right? So we picked a point of 0 enthalpy out of convenience. So we measure enthalpy relative to the enthalpies of pure elements in their standard states. So what are standard states? Well, the definition has to be a little different depending on what kind of a substance we're looking at. If the element in question is a gas, then the standard state for a gas is the pure gas at exactly 1 atmosphere of pressure. Because it might be a little different if it was at 2 or 3 atmospheres of pressure. So we have to define the pressure for a gas. If it's a liquid or a solid, we're talking about the pure substance in its most stable form. Some elements have more than one form. Carbon can be found as graphite or as diamonds. Graphite is the most stable form, and so I think it is. Don't quote me on that. One form is always more stable than the other. And then we specify, again, the pressure and temperature of interest. Usually this is 25 degrees Celsius, which is considered room temperature, so that's convenient. If we have something that's aqueous or dissolved in some other substance, then we are looking at a concentration of exactly 1 mole per liter. So the standard enthalpy change, this little superscript 0 is what tells us that it's the standard. So standard means this is occurring at standard conditions, the ones we just talked about. The standard enthalpy change is then the enthalpy change when all the reactants and products are in their standard states. Now this doesn't necessarily happen in the reaction that we're using, but that's what the standard enthalpy change is. Standard enthalpy of formation, again, we've got this degree sign, this superscript 0 indicating standard, the F for formation. Standard enthalpy of formation is when you have a reaction forming 1 mole of the pure compound from the elements. The elements then have to be in their standard states. The heat of formation for elements then is going to be 0 because we defined it that way. Any questions? Here's a table from the chapter listing some standard enthalpies of formation for different compounds. And then there's more extensive tables in the appendix at the back of the book. Let's look at bromine here just because it's first. So we've got bromine in the gas state, we have Br2 in the liquid state, and we have hydrogen bromide in the gas state. Well, just from what we've learned so far, what would we expect bromine to be as a pure element at room temperature? A liquid. Bromine is one of the only 2 elements that are liquids at room temperature. And is bromine one of the diatomic elements? It is. So the most stable form of bromine is a liquid with the formula Br2. And here we see the heat of formation for Br2 liquid is 0. That's the most stable form of the element. We defined, we said, okay, that's 0. We're going to measure things relative to that. You can make bromine atoms, but you have to put some energy into it. And so the heat of formation for a mole of bromine atoms in the gas state is 111.9 kilojoules per mole. So for every mole, you have to exert 111.9 kilojoules to do that. When HBr forms, HBr forming from its elements in their standard states, the heat of formation for that is negative 36.3. This being a negative number tells us that that's releasing energy. That's probably something that's going to happen fairly easily, as opposed to things with a positive heat of formation. Not always, but likely are not going to be spontaneous. You're going to have to make them happen. Any questions? So standard enthalpy of formation, also called standard heat of formation, because we tend to use heat and enthalpy kind of interchangeably, because at constant pressure they are the same. So standard enthalpies of formation for elements are 0. And we measure changes from that, just like we measure elevation changes compared to sea level. For most compounds, the heat of formation is negative. So if you're thinking about, the ocean, most compounds, the heat of formation is going to be, they're going to be underwater. The elevation is down. The change is going down from 0. So to make this information useful so that we can calculate what's going on, we have to understand what formation reactions are. So the standard enthalpy of formation for methane is this, and we could look that up in the table. In fact, let's do that. So methane is under carbon. Oops. Here's methane. So forming methane, minus 74.6. The unit is kilojoules per mole. So minus 74.6 kilojoules per mole. That tells us forming methane, 1 mole of it, from the elements in their standard states. So these are the elements in their standard states. Carbon as a solid, graphite, not diamond, plus hydrogen. And then we balance this so that we end up with our product and a coefficient of 1. So how do you know? Oh dear. Oh, well, I'll not say that then because it's coming up in the next slide. So these are combining elements in their standard states to make 1 mole of the compound. Well, if you're not sure what the standard state is, go look in the table and find it. So let's go back and look at carbon. So here's carbon. There's 2 of them listed, graphite and diamond. The heat of formation for the graphite is 0. That tells me that's the one in its standard state. When we write these formation reactions, we have to have, by definition, 1 mole of compound as our product. So sometimes we're going to get fractional coefficients, and that's okay. So we need to learn how to write formation reactions. So let's do this for carbon monoxide. So the formation reaction would be the reaction between the elements in their standard states. The elements are carbon and oxygen, and that's going to make carbon monoxide. But these have to be in their standard states. So for carbon, we need to specify that it's a solid and it's graphite. And then for oxygen, we'll go back and look in the table. Here we go, oxygen. So the standard state for oxygen is given here. We identify it because it's got the 0. O2. So the standard state is O2. So I've identified the elements that are needed to form this. Then I need to balance this, but I need to do so in a way that this coefficient stays 1. So I need a half, 1/2 on the O2. So we get graphite plus half a mole of oxygen to form carbon monoxide. And then here's the heat of formation. And where did we get this number? We just looked it up in the table. It's not a big mystery. Okay? Let's do an example, or 2 examples. Write equations for the formation of sodium chloride solid and lead to nitrate solid. And in these types of equations, the states are important. So we do need to include our state symbols. So let's do sodium chloride first. So that's A. So I'm trying to make sodium chloride solid, and I need to include the heat of formation. So I look at this compound and I say, well, what are the 2 elements in it? There's sodium and chlorine. So I'm going to have sodium and I'm going to have chlorine. And then I'm going to go look in the table. You do not memorize the table. The table will either be given to you or the particular parts that you need will be given. So I'm looking for chlorine. So there's chlorine atoms, chlorine molecules. That's the standard state right there, Cl2 gas. And if I look for sodium, there's sodium solid and sodium gas. Well, sodium solid is the standard state. And then while I'm here, I'm going to look up the heat of formation for sodium chloride because it asks me to include that. Negative 411.2. Minus 411.2, and that's going to be kilojoules. So sodium is a solid, chlorine is Cl2, and it's a gas. Yes?
If the equation shows it's only 1 mole, do we still need to put 411.2 kilojoules per mole?
Well, this is saying include the values of the heat of formation for each equation. You do not have to include the per mole part because that's understood. But it's asking me to write the actual number. So how would I balance this? I need to put a half in for the chlorine. Okay? Normally when we would balance an equation, we'd put a 2 in front of sodium and a 2 in front of sodium chloride and have nice whole numbers. But heat of formation, it's how much energy is involved in forming 1 mole of the compound. So let's look at this next one, just a little more involved. So I've got lead to nitrate. Solid. Okay, so what are the elements involved? Lead, nitrogen, and oxygen. So I'm going to have lead. Let's take a guess. What do we think the most stable form of lead is? Solid. And the metals are always just going to be monatomic. They're not going to be diatomic or anything. And then nitrogen, what is our guess for the most stable form of nitrogen? A gas. Is it a diatomic element? It is. So that's our guess, N2. And then oxygen, we've already looked at that one, so that's going to be O2 gas. Then we need to go back and look at the table. So lead isn't in there. Nitrogen, there we go. And Oxygen, yeah, so we guessed correctly. If someone has their textbook, could you look in the appendix at the end and look up heat of formation of lead nitrate for us? That would be helpful. So we've got our standard states now. We need to balance it. We can't change the coefficient on the product. It needs to be 1. There's 1 lead here and there's 1 lead there, so that's nice. The nitrogens, there's 2 of them, and there's 2 over there, so that's cool. How many oxygens in this? 6. So we need to put a 3 in front of oxygen. Anybody found the heat of formation? I'll find it. Okay, I tried to look it up, and I lost my writing was negative 452 kilojoules. It's in the back of the book, but I didn't have that accessible, so oops. So any questions about that problem? So the heat of formation is making a compound from the elements in their standard states. Now that is not necessarily how you would actually go about making the compound. In fact, it probably is not. But that sort of information has been tabulated and is useful. So the negative of that would correspond to the decomposition of the elements into their standard states. So if you wanted to know what's going to happen if I take that compound and decompose it into the elements, by zapping it with electricity or heating it or however is necessary, you just change the sign. Just like what we talked about with the heats of reactions. You reverse the reaction, you change the sign on the change in enthalpy. So what we're doing here is that we are, in our minds, not actually, but in our minds, we're decomposing the reactants into elements and then forming the products from their elements to find the actual heat of reaction for something that has compounds as reactants and products. So as we looked at with Hess's law, any reaction can be written as the sum of other reactions, right? And so what we're doing here is we're looking at this compound as a reactant, and we're saying, well, yeah, but we could make that from its elements, and we know the enthalpy change for that. And another reactant that's a compound, we can make that from its elements, we know what the change in enthalpy is. And then the product. And so the reactants are going to have negative of their heat of formation, and the product is going to have the same sign as the heat of formation. So the overall standard heat of formation is the sum of the heats of formation for each of the components. And so this is the shorthand version. Instead of manipulating all those chemical equations and adding the delta H's, this is the bottom line, what it comes out to be. The standard heat of reaction is going to be the sum of the heats of reactions for all the products multiplied by their corresponding coefficients, and then subtracting the heats of reaction for the reactants. Okay? Now, I think we're going to be doing an example. We're going to look at an example, and then we're going to do an example, and hopefully it'll start to come together. So this is a Hess's law diagram showing how we could make figure out the enthalpy for this. So methane plus oxygen. This is the burning of methane. You got a question?
Yeah. So kilojoules is a measure of energy, right?
Yes.
So is that is time an irrelevant aspect of that, or?
Time does not come into these calculations.
So it's the same, it's going to be constant whether or not it's in a span of 5 seconds or 5 years?
Yeah, so if you took methane, say 1 mole of methane, and you burned it in 1 second, or you burned it in an hour, the amount of energy that's released is the same.
Okay. And is that
Now, the rate at which it comes out is different. right? And so if you release a lot of energy in a very short period of time, that's like an explosion, right? And if you release it very, very slowly, you might not even notice that it's being released.
So is it the same like with endothermic reactions then? Like they just have to absorb a set amount of energy for them to become complete?
Yes. Endothermic reactions are going to be absorbing energy, and in general, time is not a real big factor in that. When we get time involved, we start talking about rates of reactions and rates at which things occur. And that's studied in Chem 1B. Yeah, so if you continue on in this chemistry series, you will learn about that, maybe more than you wanted to. That's a good question. So burning methane, this is the chemical reaction. Well, how could we figure out the amount of energy released without actually doing it? Well, we can think of this as being the sum of a series of chemical reactions. So here's our reactants, methane and oxygen. We can think of taking apart the methane. So we're taking CH4 and we're breaking it into its elements, carbon and hydrogen. And we're taking this oxygen that's already in its standard state, so that just goes along here. So to decompose the methane is positive 74.6 kilojoules. That is the opposite of its heat of formation. Okay? And then we can take these elements and we can form carbon dioxide. The heat of formation of carbon dioxide is minus 393.5 kilojoules. And then we can form the water from hydrogen and oxygen, and that's this step, releasing 483.6 kilojoules of energy. So when we add this input of energy and this release of energy together, we end up with the overall total. So that's a diagram. We can also look at it in terms of individual equations. So here, graphite plus water, plus hydrogen to form methane. This is the heat of formation of methane. You look that up in a table. And graphite plus oxygen to form carbon dioxide. There's the heat of formation of the carbon dioxide. And the heat of formation of water is hydrogen plus 1/2 oxygen. Here's the heat of formation of the water. Now, how could we put these chemical equations together to make this one?
Reverse the first one.
Yeah, we're going to have to reverse the first one so that we get methane as a product, as a reactant. We want to keep this one this way, and we want to keep that one that way because carbon dioxide and water are both products. So, can you see that it can be done? We don't really want to do it, do we? I don't have room to write it all out here. It's messy. So, we could do that. That's what we learned in the last section about Hess's law. Or we can just use these heats of formation and use that funky looking equation with the summation signs. And we can say, well, the heat of formation for carbon dioxide, that's right here, heat of formation for carbon dioxide, and there's one of those, plus 2 times the heat of formation for water, that's this guy. And then we're going to subtract the heat of formation for methane, plus 2 times the heat of formation for oxygen, which is 0. And that'll give us the same result without having to mess around with all those equations. Any questions? So standard heats of formation make it easy to calculate the amount of energy that's going to be absorbed or released, the change in enthalpy for a reaction. Now, this is occurring at standard states. And so the standard state may not be what your reaction is doing. And your particular reaction might not happen exactly as planned, right? And so these really are estimates, right? They're not exact numbers at all. Any questions? I think we have an example coming up here. Okay, so the thermite reaction. Has anybody ever seen the thermite reaction? It's pretty cool, huh? Actually, it's pretty hot. It's aluminum. You mix aluminum with rust, basically, and you get it started, and it just showers sparks and gives off a lot of energy. It's a very, it's what's called a single replacement reaction. So here we have the element aluminum, and he's going to the party by himself, and iron is coming in with a date, oxygen. And there's this big fight that happens, and aluminum leaves with the girl, and iron's left by himself, right? Sparks flew, literally. Yeah. Anyway, so this reaction, highly exothermic, use standard enthalpies of formation to find the heat of reaction for the thermite reaction. So what we're going to do is we're going to use that equation. We're going to find the heat of formation for the products and multiply them by their coefficients, and then we're going to subtract the sum of all the heats of formation for the reactants. So let me write that out. So the standard heat of formation for this reaction will be equal to the heat of formation for Al2O3 plus the heat of formation for iron times 2, because there's 2 of them. So that's the products, and then we subtract for the reactants. So we've got 2 aluminums, so 2 times the heat of formation for aluminum. And we've got 1 Fe2O3 Does that make sense? Some of these are 0, aren't they? Elements in their standard states are 0. You should always look it up in the table to confirm, but Fe here, Fe solid, that's the standard state. So that's 0. And aluminum solid is the standard state, so that's 0. So we actually have just 2 numbers we need to look up. The question is, are they in the table? I kind of think they're not. Nope. So we looked up these numbers. And so the heat of reaction is the heat of formation for aluminum, which is minus 1675.7 kilojoules per mole, minus the heat of formation for Fe2O3, which is negative 824.2 kilojoules per mole. So be careful with your negative signs. We've got negative 1675.7 minus negative 824.2. I'm going to get minus 851.5. Any questions? This will come out to be the right amount for the reaction as written because we included the coefficients when there were any. Okay, so we would write this up here. The heat of reaction, the standard heat of reaction is minus 851.5. 11.5 kilojoules. Because it's for the reaction as written. Questions?
So that was just rust and aluminum?
Just rust and aluminum, yeah.
I'm gonna try that.
You're gonna try that? Yeah,
So this, can you go back to the other slides?
that one.
So this temperature, is this just for the arrow portion? Or what? Like where does
Temperature?
this start at? Because you use the kilojoules of this pre-existing material. So is this kilojoule, is this energy only energy in the reaction, or is this energy that's already stored by this compound that's already been created?
Okay, that's a good question. First, let me ask you about your use of the word temperature. Because we're really not talking about temperatures at all
Well,
here.
yeah, no, I meant
Okay.
to say energy.
Just checking.
Yeah.
So, we say that aluminum is not going to take any energy to form, right?
Right.
And this iron oxide, there was an energy change or an enthalpy change involved in its formation. So that was the minus 824.
So
If you form iron from Fe2O3 from iron, solid, and oxygen, that's going to release 824.
right, but is that's not part of the reaction? Or is
No,
it?
that's not occurring, but there is energy that is stored in the chemical bonds, right? And so this required 824 to form, released, and this releases 1675. If I take this Fe2O3 and instead of forming it, I decompose it, which is what we're really doing here, that's where I have to, it's going to absorb 824 kilojoules per mole. And so overall, this is being absorbed, the 824, and this is being released. And so the difference is this.
Okay, so this is more like a net change in energy.
This is the
then?
net change. This is the change occurring from where this started to where it ends up.
Okay, instead of the amount of energy to actually complete the whole thing. Okay.
Well, if you're starting here, I mean, this has already undergone some changes, but those already happened,
Exactly.
right? And so when these react, this is the net result.
Right. Okay.
Yeah. Any other questions?
Well, can you go back one slide, really?
I think I can.
Oh,
That one?
yeah,
Okay.
okay.
Never mind.
No, I mean, like, I was noticing the net reaction on this one, really close to the other one, but it's for 1 mole, right? So 1 mole of this is a lot lighter than a mole of the other.
Well, a mole is a number of particles, regardless of how heavy they are.
Right, but these are that particular particle. The other one is, oh, never mind. I'm confusing myself.
That's okay. You're confusing me too. So
Okay.
you're doing a good job.
It's because I've seen both reactions, and the other one's a lot, it feels like it throws off a lot more energy, but then again, you're using a lot more of the substance.
Okay, I see what you're getting at.
That's what I was,
So this one ends up releasing 802 kilojoules, and this one was releasing 851.
but these are heavier elements.
They are heavier, but what's important is it's the number of molecules.
Okay.
And there's really no correlation between mass and amount of energy released between different substances. But we also find that the amount of heat released or absorbed for a given reaction depends on the identity of the individual reactants and products and not on how much they are, if that makes sense. So I think it's kind of coincidental that these both ended up being negative 800 something. But yeah, the heats of reaction all over the place. Some of them are positive, some of them are more negative than this. It just varies a lot. So let's look at this one. Chemical hand warmers. I used these at a football game, a couple of football games last fall. So you remove them from their plastic wrapper. If the plastic wrapper is broken, don't buy it. It's already done. The reaction happens between oxygen from the air, and all that's in there is little tiny iron pieces, really finely divided iron. And so basically you're using the rusting of iron to keep your hands warm. And it's, quite non-toxic. It would be bad if you breathed in the fine iron filings, but it's not toxic or anything in the normal sense of the word. So we're asked to calculate the standard enthalpy of reaction for this reaction, considering that we have a hand warmer with 15 grams of iron powder. So let's look at this reaction. How would we calculate delta H for this reaction? Well, we take the heat of formation of the product times 2, and we'd subtract the heat of formation of iron times 4, and the heat of oxygen times 3. Those are both elements, though, aren't they? So delta H for the reaction as written is then twice the heat of formation because of the 2. So we have the heat of formation, it was minus 824.2. So delta H for this reaction is minus 1648.4 kilojoules. I would base my significant figures on the heat of formation, which had 4, and so I'm going to underline that 8. So that's delta H for this reaction as written. Everybody okay with how I did that? How do we figure out how much energy is released if 15 grams of iron powder reacts? So 15 grams of iron to moles of iron, and then we know that we're going to get this much for every 4 moles of iron. So it's stoichiometry with energy. So we're going to take our 15 grams of iron powder, and I'm going to convert that to moles of iron. So I want the molar mass of iron down here, 55, I believe it's 55.85. Yeah, grams. And grams of iron cancel out. And then I don't need to go to moles of anything else because this heat of reaction applies to every single thing. So it's this amount of energy, negative 1648.4 kilojoules for every 4 moles of iron. Moles of iron cancel out. 15 divided by 55.85 times negative 1648.4 divided by 4. And I'm coming up with minus 110 point, let's see, 3 sig figs. 68. And so I'd round that to minus 111 kilojoules. So, do I want, if this is a mastering chemistry question, do I want to include the negative sign in my answer?
Yes.
Is there a direction indicated with words? What about this word? Produced. Produced implies that the energy is coming out, that this is an exothermic reaction. So mastering chemistry would probably want you to say 111 kilojoules. 111 kilojoules of energy are produced when 15 grams of iron powder reacts. Any questions?